Hi, this is lesson 5 of unit 7 in chemistry, and in this lesson we're going to go ahead and talk about titration as well as the pH scale. For our lesson objectives, students will be able to solve for the concentration of an unknown substance using the process of titration. Also, students will be able to solve for the pH of a substance using its hydronium ion concentration. Let's go ahead and get started.
Let's start with titration. Titration is an analytical method in which a standard solution is used to determine the concentration of another solution. In other words, you get a solution whose concentration you do know, and you mix it with a solution whose concentration you do not know, and that method will allow you to figure out that unknown concentration. There's a picture on the right on the slide that tells you how titration looks. In it, you would mix using a burette, which is the glassware on the top, and you would mix a known solution into the unknown. When you see a color change, like you see right there, that bright pink or purple color, then you have achieved titration, the endpoint, and you calculate how much volume of the known concentration you added to the unknown, and you figure out the concentration. We'll do some calculations on that shortly. Now, what is a standard solution? That is a term used for a solution whose concentration you do know. Next, what is an indicator? The indicator is what actually changes color. A weak organic base or an acid whose color differs from the color of their conjugate acids or base, that is an indicator. And there's some indicators that can change from clear to pink, like you saw in the picture, or all sorts of colors of the rainbow to give you an idea of what the pH is for that solution. Now, a buffer system. Sometimes you want to keep the pH from changing in a solution. So what you would do is add a buffer system. So right here on the slide states that a buffer system is a solution that can absorb moderate amounts of either acids or base without any type of significant change in the pH. Pools often have a buffer system because you don't want a swimming pool to get either too acidic, it would make your eyes hurt, or maybe you don't want the pool to become too basic, it will dry out your skin. So you want to go ahead and keep it right around neutral. So you would add a buffering system to a swimming pool to keep it from changing either up nor down. All right, now up next, let's go ahead and solve some problems involving titration.
In this titration problem, we're asked the following question. What is the volume of a 0.2 molar LiOH solution required to neutralize 0.025 liters of a 0.4 molar HBr solution? So our HBr is hydrogen bromide or hydrobromic acid, and our acid is going to be neutralized by the LiOH, which is lithium hydroxide. So how much of the lithium hydroxide do we need to neutralize the solution of hydrobromic acid, which is 0.025 liters in volume and 0.4 molar in concentration? So what I'm going to go ahead and do is put the information for the acid here on the left, and so our concentration, it is 0.4 molar, and its volume, we're going to multiply times its volume, is 0.025 liters. Now on the other side, we're going to go ahead and put the concentration in molarity of the base, the lithium hydroxide, which is 0.2 molar, multiply times the volume, which is what we're solving for. So to solve for this titration problem, there's really only one step, which is we're going to go ahead and divide both sides by 0.2 molar, the concentration of the base. And when we do that, that's going to isolate the V2, which is the volume we're solving for. And my calculator, I'm going to go ahead and put 0.4 multiplied times 0.025 divided by 0.2. So it's going to go ahead and give us 0.050 liters of the base that will be needed to neutralize the acid. All right, now let's go ahead and take a look at a second problem. In this example, they ask you, what is the concentration of a solution of NaOH, which is sodium hydroxide, if that's a base, if 0.035 liters of a 0.08 molar solution of HCl are needed to neutralize 0.025 liters of the base? All right, so now our acid, HCl, is hydrogen chloride or hydrochloric acid. Now that is the acid we want to go ahead and neutralize. It has this volume, 0.035 liters, at this concentration, 0.08 molar. So again, we're going to do much the same as before. And it's going to go ahead and be the concentration of the acid. I'm going to put it here on the left. It's going to be 0.08 molar. And the volume is 0.035 liters. Now on the other side, we're going to go ahead and put the base. They tell us that we have this volume of 0.025 liters. So what concentration must it be so it can neutralize the acid? So I'm looking for the concentration, in this case M for molality. And now it's going to go ahead and be the volume 0.025 liters. Again, I want to solve for the molarity, so I'm going to go ahead and divide both sides by 0.025 so I can isolate that M2. That will cancel out, giving us M2 is 0.08 multiplied times 0.035 divided by 0.025. It's going to go ahead and give us 0.112 molar. And that will be the answer for example 2.
Next, let's go ahead and talk about ionization of water. So what is ionization of water? Water on its own will self-ionize. It will develop a charge. That's what an ion is an atom or molecule with a charge. So water will self-ionize. How does it do that? If you look at the molecule at the bottom, you have two water molecules there. And what they will do is one will transfer hydrogen to the other, giving us one will develop an H3O plus, which is called a hydronium ion. And notice there's the ion has a positive charge. And the other one will become a hydroxide ion, and there's the negative charge. So it will self-ionize. How do we know that this is happening? Well, it was found through conductivity experiments. That means that they're running electricity through the water, and it's able to go ahead and give us an idea of how much this is happening. It only happens to a very small amount of water molecules. How much does it happen? Well, it happens at this rate at 1 × 10⁻⁴, which is a very, very small number. And that is our Kw. That is the water constant. So the ion product constant for water, Kw, is calculated by this formula. If you multiply all of the hydronium ions times all the hydroxide ions, it will always equal 1 × 10⁻⁴. That is our constant to this formula at 25 degrees Celsius. So all of our formulas are going to assume to take place at that temperature, 25 degrees Celsius. And one more time, the constant is exactly that, a constant. So you always use this number, 1 × 10⁻⁴, for this formula.
In example 3, we're given the following question. Calculate the H3O plus concentration, that's the hydronium ion concentration of a solution with a hydroxide ion concentration of 2.3 × 10⁻⁴ molar. Now, for this problem, we use this formula. So that'll be the hydronium ion concentration multiplied times the hydroxide ion concentration will give you this constant for water, which is 1.0 × 10⁻⁴. So this value here is a constant. So while solving this type of problem, you always use this value. So we're going to go ahead and substitute for the hydroxide ion 2.3 × 10⁻⁴. So I'm going to go ahead and do that first. Substitute 2.3 × 10⁻⁴. And now I want to go ahead and isolate the hydronium ion. So I want to get rid of the 2.3 × 10⁻⁴. So to get rid of a number, I divide it by itself. And what I do to one side, got to do to the other. So that's gone, giving us hydroxide ion concentration. It's equal to this number divided by that. So let's go ahead and plug them into a calculator. So it's going to be 1 × 10⁻⁴ divided by 2.3 × 10⁻⁴. The answer for this problem is 4.35 × 10⁻11 molar. That's our hydronium ion concentration. In the next example, they go ahead and they ask us a similar question, but here they're asking calculate the hydroxide ion concentration, and they give you the hydronium ion concentration, which is 4.5 × 10⁻11. So in this problem, it will set up much the same way, same formula, and again, the 1 × 10⁻⁴ is a constant for water. So you always use this number here. They give us the hydronium ion concentration, so I'm going to go ahead and substitute it in. It's going to be 4.5 × 10⁻11 times hydroxide. It's equal to 1.0 × 10⁻14. And you're going to go ahead and solve this problem much the same way, where we want to isolate the hydronium ion, so we need to get rid of that number. So to do that, we're going to divide it by itself. And again, what you do to one side, you have to do to the other. And there you have it. All right, so it's going to bring down the isolated hydroxide ion. And we're going to go ahead and divide both of these numbers to get our answer. So it's going to be 1 times 10 to the negative 14 divided by 4.5 times 10 to the negative 11. So it's going to give us an answer which is 2.22 times 10 to the negative 4 molar. That is our answer. It is in scientific notation. That's what my calculator gave me, scientific notation, though sometimes the calculator does give you the answer not in scientific notation. It'll write out the whole number. So this same answer could look as this: 0.000222 molar. And both are the same number, just one of them is in scientific notation. Either one is the same number, so therefore both of them are the correct answer. All right, that takes care of example 4.
Next, we're going to go ahead and talk about pH and pOH. pH is a scale used to specify either the acidity or basicity of an aqueous solution. Now, on the pH scale, it goes from 0 to 14, neutral being 7. A substance that has a pH of less than 7 is said to be acidic. A substance that has a value more than 7 is said to be basic. Another word for basic is alkaline as well. Measuring the pH is done by calculating the negative log of the hydronium ion. So that is the equation right here in red to solve for the pH. pH equals the negative log of the H3O plus concentration. Now, what if they give you the pH and you want to go ahead and figure out if a substance has a pH of, let's say, 3.5, what is the hydronium ion concentration? That same formula is rearranged to now the second formula, where you have the hydronium ion concentration is equal 10 to the power of negative pH. Whatever the value of the pH is will be substituted for the exponent. Next, pOH is calculated by measuring the negative log of the hydroxide ion concentration. And also for solving for the hydroxide ion concentration, if you're given the pOH, then what you would do is you would do 10 to the negative pOH. Next, let's go ahead and take a look at some examples on how to use these formulas.
In example 5, we're asked the following. Find the pH of the following substances. So they give us a soft drink that has a hydronium ion concentration of 3.2 times 10 to the negative 4, coffee with a hydronium ion concentration of 6.3 times 10 to the negative 6, and finally detergent, which has a hydronium ion concentration of 3.6 times 10 to the negative 11. So to solve for the pH, we're going to use this formula. pH is equal to the negative log of the hydronium ion concentration, which is given here for part A, B, and C here. So what I've done is I go ahead and I substituted part A, B, and C, the value for the hydronium ion concentration here, and all you've got to do is plug it into your calculator and place negative log of the value that was given to you. Once you press that negative log of this number, you press equal, you get the answer. So the pH for the soft drink is 3.49, so it is acidic. The pH for the coffee, it is 5.2, so it is acidic, though not as acidic as the soda. And the pH of the detergent is 3.9 times 10 to the negative 11. Negative log of that value will give us a pH of 10.41, making it basic or alkaline. All right, that is example 5. In example 6, we're asked to calculate the pOH of the following substances. We have solution A, B, and C, and they have a concentration of 8.2 times 10 to the negative 3 molar, 4.5 times 10 to the negative 6 molar, and 1.0 times 10 to the negative 11 molar. So to solve for the pOH, what you would do is you get the negative log of the hydronium ion concentration as they're given to us right here. So you'll see that I got negative log and I substituted each of the 3 values that they gave us here, here, and here for A, B, and C. And all you do is put in your calculators negative log of this number, same here, same here. So for letter A, the pOH is 2.09. For the letter B is pOH is 5.35. And finally, pOH for letter C, it is 11.0. So those are the values. Now for pOH is the opposite of an acid. So in an acid, for the pH, it's going to go ahead and be a lower value, will give you more acidic. But here, a lower value will give you more basic. So the more basic between A, B, and C will be letter A, and this will be the most acidic out of these three. That is example number 6. In example 7, we're asked the following question. Calculate the hydronium ion concentration of the following substances. And notice that they give us the pH for each one of these for grapes, bread, and ammonia, which are 4, 5.5, and 11.1 respectively. Now, that is the opposite of the previous problem we have done before. We got the hydronium ion concentration and we solved for the pH. Now they're giving us the pH and we're going to go backwards. So we're going to use the same formula, but we're going to modify it a little bit. So here's our formula to solve for the pH, but now we want to solve for the hydronium ion concentration. So I want to isolate the hydronium ion. So first step, I'm going to go ahead and get rid of the negative. So multiply both sides by -1. So now we have this negative, that's positive. Next, how do we get rid of a log? Anti-log. The anti-log is 10 to the x. So when we do that, the log goes away, isolating the hydronium ion, and then 10 to the x is really the negative pH. So it becomes 10 to the power of negative pH. Alright, so this is our formula now. They're both the same formula, just rearranged. This is for solving for pH versus this one solving for the hydronium ion concentration. So now for part A, B, and C, what I've done now is put the hydronium ion concentration here, 10 to the negative. So they give us for A, the pH is 4, so I substitute the pH of 4, put it in my calculator, give me 1 times 10 to the negative 4 molar. Next, they give us for bread a pH of 5.5, so it's 10 to the negative 5.5, will give us 3.2 times 10 to the negative 6 molar. And finally, the pH of ammonia, which is used as a household cleaner, it is 10 to the negative 11.1, so it gives us that answer of 7.9 times 10 to the negative 12 molar. Alright, so that is example 7.
Next, let's go ahead and take a look at the formula for ionization of water and how we can use it to derive a new formula. So a new formula here in red, it is pH plus POH equals 14. Now that is the same formula as the ionization of water. If we go ahead and we get the negative log of the hydronium ion, that's going to give you the pH. The negative log of the hydroxide ion is going to give you the POH, and the negative log of 1.0 times 10 to the negative 14 gives you 14. So as you can see, the top formula here in black and the bottom formula here in red are the same formula after you get the negative log for each of those values. Now let's go ahead and take a look at an example on how to use this formula.
In example 8, we're asked the following. Find the POH, the hydronium ion concentration, and the hydroxide ion concentration of a solution with a pH of 5.8. So now we're missing all of these and we're only giving one the pH. So I'm going to begin by finding the POH. So I'm going to do so by using this formula. pH plus POH is equal to 14. So I'm going to substitute the pH right here, 5.8 plus POH equals 14. So all I'm going to do now is just isolate the POH by subtracting 5.8 from both sides. So we end up with POH is equal to 14 minus 5.8 gives us a value of 8.2. So that is our first answer, 8.2. Next, I have the POH. I can use that to solve for the hydroxide ion concentration. So hydroxide ion concentration is equal to 10 raised to the negative POH. So I plug it in. So it's going to be negative 8.2. So therefore, a hydronium ion concentration is going to be 10 to the negative 8.2. 6.3 times 10 to the negative 9 molar. So that's our hydroxide ion concentration. Next, we still need the hydronium ion concentration, the H3O plus. So we're going to go ahead and use this formula to solve for it. We're going to have H3O plus multiplied times OH minus will give us 1.0 times 10 to the negative 14. Alright, so now what I'm going to go ahead and do is substitute this value here. So it'll look like so. 6.3 times 10 to the negative 9 equals 1.0 times 10 to the negative 14. And now what I'm going to go ahead and do is isolate the hydronium ion concentration. So I'm going to divide by 6.3 times 10 to the negative 9 on both sides. That will cancel this out, giving us just a hydronium ion left on the left side of the equal sign. And on the right side, we're going to go ahead and get 1 times 10 to the negative 14 divided by 6.3 times 10 to the negative 9. Gives an answer of 5.6 times 10 to the negative 6 molar. And that is our hydronium ion concentration. Alright, so there we have it. Those are all our answers. That is how you solve example 8. This brings us to the end of lesson 5 of unit 7. Thank you for watching.